In other videos, we had started talking about the types of bonds that might form between atoms of a given element. For example, if you have two metals forming a bond, well, you are going to have a metallic bond. If you have two nonmetals engaged in some type of bonding activity, this is likely to be a covalent bond. And the general rule of thumb is if you have one metal and one nonmetal, that this is likely to be an ionic bond. These are the general rules of thumb. What I want to do in this video is to better appreciate that bonding is really more of a spectrum. There are bonds, and we've talked about things like polar covalent bonds, that start to look a little bit more and more ionic in nature. And so that's what we're going to talk about in this video, and think about it in the context of electronegativity. Just as a reminder, we talk about electronegativity in many videos, but this is the property of an atom that's in a bond to hog electrons, to want the electron density to be closer to it, for the electron pairs to spend more time around that particular atom. So something with a high electronegativity is going to be greedier with the electrons than something with a low electronegativity. We could think about the spectrum between, at this end, you have ionic, and at this end, you have covalent. And one way to think about it is, at the extreme left end, you don't have much difference in electronegativities. Both atoms that are participating in the bond are roughly equal in how badly they want the electrons, while in an ionic bond, you have a very big difference in electronegativities, so much so that one of the atoms swipes an electron from the other. So one way to think about it is, let me draw a little bit of an arrow here. So this is increased electronegativity difference as you go from left to right. And someplace in the middle, or as you go from left to right, you're becoming more and more polar covalent. So for example, if you have a bond between oxygen and hydrogen, these are both nonmetals. So this will be a covalent bond by our general rule of thumb. And actually the division between metals and nonmetals, I'm going to make it right over here. It's this blue line is one division you could view, although the things that straddle it are a little bit more interesting. But oxygen and hydrogen are both nonmetals, but you have a pretty big difference in electronegativities. This right over here is electronegativity measured on a Pauling scale, named after the famous biologist and chemist Linus Pauling. And you can see on that scale, oxygen is a 3.44, one of the most electronegative atoms. Electronegativity trends, we talk about in other videos, goes from bottom left to top right. The things at the top right that are not the noble gases, these are the ones that really are greedy with electrons. And oxygen is one of the greediest. While hydrogen, it's not electronegative, but it's lower at 2.20. So in this scenario, those electrons are going to spend more time around the oxygen. If they spend an equal amount of time, that oxygen might be neutral. But since they're spending a little bit more time here, we'll say that has a partial negative charge, the Greek lowercase letter delta. And on the hydrogen side, because the shared electrons are spending more time around the oxygen than around the hydrogen, you would have a partially positive charge right over there. And so this would be a polar covalent bond. Maybe on the spectrum, it sits right over there, depending on how you view this scale. Now the other question says, okay, this is a spectrum between covalent and ionic. What about metallic? Well, metallic bonds are in general going to be formed if you have two things that are not so different in electronegativity, and they both have reasonably low electronegativities. So that's why things on the bottom left right over here, if you have two of these forming bonds with each other somehow, that you're likely to have metallic bonds. And that makes sense because in metallic bonds, you have all the electrons kind of mixing in a shared pool, which gives some of the properties like conductivity. And so if you have a lot of things that are fairly similar in electronegativity and they're all low in electronegativity, they might be more willing to share those valence electrons in a communal pool.